In this video, we'll look at section 2.2, covering the division algorithm and the Euclidean algorithm. So again, this might be a review for some of you. The division algorithm is something I think we know. Well, at least how to divide two numbers. We certainly know an algorithm for that. But specifically that we can find two numbers. So if we divide A by B, then we get some quotient Q and a remainder R. But specifically, we get a remainder that's smaller than the thing we're dividing by, so we're smaller than b, and also a positive remainder. So just to give you an idea of, and that these numbers q and r are unique. So to give a quick idea, let's suppose a is 39 and b is 14. So we're dividing 39 by 14. Now, just to pick some random numbers for q and r, there's a lot of different possibilities, of course. We could say if we make q equal to 1, then 14 times 1. To make this true, we'd have to add 25. So we could say, like, with a quotient of 1, we get a remainder of 25. We could use a quotient of 2. That gives us a remainder of 11. Or we could use a quotient of 3. That kind of goes too far. Gives us kind of a remainder of a minus 3. But there are a lot of different possibilities, a lot of different pairs of q and r, of course. But of course, the one that we want is the one where the remainder is smaller than the thing we're dividing by. So that only happens here. And so our claim in this theorem is that that's unique, that you get a unique q that gives you a unique remainder between 0 and b. Again, this might feel obvious because we're pretty used to dividing numbers and what we get as a remainder, but how do you prove such a thing? So whenever you want to show something exists and is unique, you want to prove those things separately. So first we'll prove the existence of a pair q and r that satisfies this, and then we'll show the uniqueness. So the first stage of this, first phase, is the existence part of the proof. And a lot of the time through this section, we'll be seeing the well-ordering principle. So remember what that was. If you have a non-empty set of positive integers, or at least integers that are bounded below, there is a smallest element within that set. So we're going to start with that. We'll let S be the set we get by taking A and subtracting multiples of B. So A minus KB. But, you know, that would be like the 25, 11, and minus 3 would be a couple elements in this set if this was 39 and this was 14. But we don't want the negative numbers. So we want to run through all possible integers. So k is an integer. But we also want that the result, 8 minus kb, is non-negative. So we wouldn't be including the minus 3 in this. We'll be including the 11 and 25 and any other ones that we get that are non-negative. So we've created a set of at least non-negative integers. So we know it doesn't sort of go down infinitely in the negative. So it is bounded below at least by 0. But we do have to show that this is a non-empty set. Again, this might feel obvious, but the proof of it requires a little bit of work. So we first want to show that this is a non-empty set. And notice in the theorem, a and b are integers, and b is the only one that's a positive integer. So a could be 0, a could be a negative number. So we have to take those cases separately. So we'll first look at a being greater than or equal to 0. This one's the easy case, because we can show it's non-empty by just letting k be 0. So in this case, we let k be 0, and that makes a, which is greater than or equal to 0, so that puts it into S. So in this case, we would say a is an element of S, so we certainly have the non-empty condition. But if it's if a is a negative number, we have to think a little bit harder about what value of k we need to make sure that we get a non-negative number in this set. And There are many options, of course, but maybe the easiest option is just pick k to be 2a. And let's see why that's the case, or why that works. So if k is 2a, put that in for k. So you have an element, or a potential element in this set of a minus b times 2a. Factoring out the a is this a1 minus 2b. And I claim this is a positive number because a is a negative number, and 1 minus 2b, if b is a positive number, then 1 minus 2 times it would be a negative number as well. So the product of two negative numbers is positive, and neither of them can be 0. So that gives me, again, an element in the set. This element here, a1 minus 2b, would be an S. So in either case, we get a non-empty set. So now we can use the principle of well ordering. So by well ordering, it must have a minimal element. S contains a minimal element. Say R. Well, it is going to be the remainder that we want. And by definition, R looks like one of these. So we'll say that the K that produces that R, we'll just call it Q. So that means R is equal to A minus some multiple of B. So we'll just call that K Q, just because that's what it's going to end up being. So, moving that back over, we do get this part of the theorem. So this implies that A is BQ plus R. And we know R is belonging to this set, so it is at least greater than or equal to 0. That's one part that we wanted. And R is greater than or equal to 0. What we don't know yet is that we need R to be less than B. So suppose, for the sake of contradiction, I won't put it this time, but suppose that R were greater than or equal to B. That's certainly still possible, but let's rule it out. Then, if I look at R minus B, that's a positive number, or non-negative. But it's also, if I subtract B from both sides here, it's also equal to A minus B times Q plus 1. And so, since this is a non-negative number, this is also non-negative. Well, that means that's a potential K, so it belongs to S. So that means R minus B belongs to S, but that is something that's less than R, which is going against the minimality of R. And R minus B is less than R, which is a little contradiction here. So that means that contradicts this, R being greater than or equal to B. So that implies that R is actually between 0 and B, and not equal to B. So that guarantees our existence. And I don't have much room here, but I'll try and squeeze in the uniqueness part of the proof. So for uniqueness, now we suppose that there are two pairs of Q and R that satisfy this, where R is still between 0 and B. So suppose A can be equal to BQ plus R, and say BQ prime plus R prime. So we have two different representations, or two different pairs of Q and R that appear to work, where both of those remainders, R and R prime, are between 0 and B. Now, without loss of generality, we can say one of them is bigger than or at least as big as the other. again, we want to show that they're equal. But without loss of generality, we'll say R is at least as big as R prime. So since these two are equal to each other, I can rearrange this equation here to put sort of all the b's on one side, all the r's to the other side. So you end up with, and then factoring out the b. So you get b q minus q prime is equal to r minus r prime. Let's see, make sure I do that. It's r prime minus r. I suppose it doesn't matter. Yeah, we want this to happen. So I'll put this on this order and then just switch this order. It's just a difference of a negative sign. But we want this to be a positive number for our argument. So we do have b times something as r minus r prime. So b divides r minus r prime. But r minus r prime, well, we just assumed without loss of generality that r is at least as big as that, so that's at least 0. And it's no more than r, because these are two positive numbers, and if I subtract, it can't be any bigger than r, or I'm subtracting a smaller number from r, so. And then r itself is less than b. So if I look at this quantity here, it's in between 0 and b, but it's a multiple of b. Well, there's only one way for that to happen. It has to be 0. So this condition here is telling us that the only multiple of b that's possible between 0 and b, not including that b, must be 0. So if the difference between r and r prime is 0, that means they're equal. So r equals r prime. And then coming back to here, if this side is 0, b is not 0, so that means this is 0. So that also implies that q is equal to q prime, which satisfies our uniqueness, because we assume that there are two potentially different possibilities here, but they ended up being the same. Okay. Our next theorem involves the GCD, or the greatest common divisor, of two numbers, a and b. So a and b are both non-zero integers here. And the theorem says that I can find two other integers, r and s, where the GCD of a and b is some combination of, or some what we'd call a linear combination of that a and b. So a times some integer r plus b times some integer s. So in other words, you can sort of create the GCD by just adding multiples of a and b together. And the GCD is unique. So once again, an existence and uniqueness theorem here, so we need to prove both. So we'll start again with existence. And the proof follows the last theorem pretty closely. We'll again come up with a set, this time a set of all possibilities here. So we'll let S be all the linear combinations of a and b. So a times, say, j plus b times k, where j and k can be any integer. But once again, we need that this quantity is non-negative. Particularly in this case, we actually want it to be positive. So we want aj plus bk to be positive. So that way we do have a set of actual numbers here. Now, I'm not going to show the non-empty part of this. I think this one's a little bit clearer. They are non-zero integers, so you could pick one of these to be 0 and the other to be either 1 or negative 1, depending on what makes it positive. So like if b was a positive number, pick k to be 1, but if b is a negative number, pick k to be negative 1, and the other one to be 0. You're certainly getting numbers in this. So a and b belong to this set, or minus a minus b, depending. So it's certainly not empty. So we'll just skip to using the well-ordering principle. So by well-ordering, S has a minimal element, which is going to end up being our GCD, so we'll call it D, which is usually the letter we use for the GCD. So S contains a minimal element. Say D. And that D must be of that form. And so this time we are going to use the R and S as the particular values of J and K. So AR plus BS. So some combination of A's and B's create this D that's minimal. So now we need to show that it's at least a common divisor. So we have to show that it divides A and also divides B. So we'll start by showing that it divides A, and so there's no specialness for A and B here. So once we show that it divides A similar argument will show that it divides B. So we're going to show that D divides A. So how do you show two numbers divide each other? Well, that's where we can use the division algorithm. We know by the division algorithm that no matter what two numbers I have, I can find a unique Q and R, and where that R is smaller than what you're dividing by. So what we can do is use that division algorithm and eventually show that the R, the remainder, is 0, which would imply that they divided, or that D divides A. So using by the division algorithm, we can divide A by D, so we get some Q and R. So A is D times Q plus R. And we're already using R up here, so we'll call it R prime. Where that remainder, R prime, is between 0 and D not equal to D. Now what we actually want to show is that R prime is 0. So for a contradiction here, let's suppose that it's in that interval but not 0. So suppose that it's strictly between 0 and D. So if we can get a contradiction from there, the only other possibility is that it's 0. Now let's solve this equation for R prime. So R prime is A minus DQ. And then you could substitute in what we know D is. D is AR plus BS. And now sort of doing the algebra here so that we get this as multiple of A plus a multiple of B. We get this as A times 1 minus QR plus, and then B times a negative S. So writing it in this way, we see that it belongs to S because it is R. It is this R prime here, so it's a positive number. And it's a combination of, linear combination of A and B. So this belongs to S. But this is a contradiction because D was supposed to be the smallest element in S. And now we have something that's smaller than D. Or, yeah, smaller than D that's in S. So this is a contradiction. So that means R prime is 0. Therefore, R prime is 0, which, plugging that in here, gives you that A is D times Q, but that shows what we wanted to, that D actually divides A. And so you get a similar argument for dividing B. So you can go through the same argument here, just change the A to B. Okay, next we'll show the uniqueness of this. And this also ends up showing that it's greatest. So all we've really shown is that there's a common divisor. But to show it's the greatest, or that you get a unique greatest one, suppose you have two that are greatest common divisors. So suppose D and another D, so say D prime, are both greatest common divisors of A and B. That sounds silly to say, but at the moment we don't know that a greatest common divisor is unique, so there could be more than one. So saying two things are greatest common divisors is fine. But we will show that it is actually unique. So what you need to show is that they divide each other. Or the strategy we're going to use here is that we'll show that D divides D prime and D prime divides D. Well, if that happens, we're talking about integers here, or positive integers here, so they must be equal to each other. So we'll start with showing that D prime divides D, but we'll only show that side of it because it's, again, a similar argument to show that D divides D prime. So from this, because D prime is a common divisor of A and B, A is some multiple of D prime, so say D prime times H, and B is D prime times some other number, say K. That's just being a common divisor of A and B. Now, coming back to D, we know what D looks like. We just showed the existence of this linear combination. So D looks like AR plus BS. But now I can replace the A and B in here by these two. So this looks like D prime H R plus D prime K S, which we can factor out the D prime. So D prime HR plus KS. So looking at what we have now, we have that D is a multiple of D prime. So this implies that D prime divides D. And similar argument tells us the other way around. So go through same argument. This time you'd have A is D times some, say, H prime maybe, and sorry, this is supposed to be multiplied. B is D times that, and then you have D prime on this side looking like that. And you go through the same thing just with D and D prime switching places. So similar argument. Gives that D divides D prime, but that means that they're equal. So there is, in fact, just one greatest common divisor of any two non-zero integers. Next, we're going to look at an algorithm for finding the GCD. And normally you'd use the Euclidean algorithm, but I want to show you the extended Euclidean algorithm, which not only gives you the GCD, but also gives you the linear combination that provides that GCD. So this algorithm will give you what the GCD is, and it'll also tell you what multiples of A and B you have to put together to get that GCD. So we'll do 14 and 39 again. It's pretty clear that the GCD here is 1. So I should be able to find a linear combination, say 39 times U plus 14 times V, that equals 1. So our goal here is to find what that U and V are. So the way the extended Euclidean algorithm works, you set it up in this way. The U and V are this U and V here. R and Q are just like the R and Q from before, remainders and quotients. And so you'll have these 4 columns. First you put these two numbers, so 39, well, what combination of 39 and 14 give you 39? Well, 1 times 39 and 0 times 14 makes that work. So we're going to be recording, this is 39 times this number, 14 times this number, should give you this number on this side at all times. So with 14, well, that's 0 times 39 and 1 times 14. So it'll always start off in this way, where you have A and B here, and you have kind of like an identity matrix sitting here. So that's the setup for the extended Euclidean algorithm. Now you start dividing. You say, well, how many times does 14 go into 39? Well, it goes in twice. We'll put a little dotted line here because these quotients don't really affect things at the very end. And so what you do now is whatever you got as a quotient here, you'll multiply by this row and subtract this from this row. So 2 times 14 is 28. Subtracting gives you an 11. Multiply this by 2, which is still a 0, so 1 minus 0 is 1. But be careful here, 0 minus 2 is a negative 2. So now at this line we have that 11 is 39 times 1 plus 14 times minus 2. So again, at every stage, you get this number as that linear combination of 39 and 14. And then you keep going. Now we're going to divide 11 into 14. That only goes in once. And so here we just subtract. If it's just a 1, you just subtract down. So that's a 3. Subtracting gives you a minus 1. Subtracting gives you a positive 3. Keep dividing. 3 into 11 goes in 3 times. So 11 minus 9, so multiplying this row by 3 gives you 2. Notice these numbers always go down because they're the remainders you would get by dividing this number by this number, which must be smaller than that number. So these numbers always go down. So this algorithm will terminate. Same thing here, 1 minus negative 3, so 1 plus 3 is 4. Minus 2 minus 9 is a negative 11. Now divide these two. This will be our last division because this will just give us a 1 when I subtract, or it goes in one time, and when I subtract I get a 1. So here, if I subtract, I get a minus 15. Subtract here, I get a 14. And you're done either when you get a 1, when the GCD is 1, but if the GCD is not 1, at some point you'll get a 0, and then the GCD was the step before that. So like if I ended at this 3 and then the next step was a 0, then that would mean that 3 was the GCD. And these are the numbers, right? So we've concluded that 39 times minus 5 plus 14 times, it's 14 times 14. So the V is 14, is equal to 1. So we found that linear combination to give us the GCD. Let's try it with some bigger numbers here. Go through the same process. So R, U, V, and Q. So first we have the setup that looks like the identity matrix here. Okay. And then you divide. So this might be hard to notice, but if you multiply this by 2, it's already over 300, so it only goes in once. So we're just going to subtract here. This gives us 69, 1, and minus 1. Now this one goes in twice if I divide, so I get a Q of 2. So I have to multiply this row by 2 and subtract from this row. Here we get 27, 0 minus 2, minus 2. And 1 minus 2 is a 3. Go again, 27 into 69 goes in twice. So multiply by 2, you get a remainder of 15. 1 minus 4 is positive 5. So you notice the negatives here kind of just alternate sides as you go. So minus 7, if I do minus 1, minus 6. Next, this only goes in once. So I just subtract this time, so I get 12 minus 7 and a 10. This only goes in once as well, so I get a 3, positive 12, and negative 17. And finally, that goes in 4 times, but that gives me a remainder of 0. So that means I don't care what happens if I were to subtract here. I only care about this line here. So this means that the GCD is 3. So let's get our conclusions here. So our conclusions are the GCD of these two numbers is 3. And in particular, if I take 234 times 12 and add that to 165 times negative 17, that gives me that GCD of 3. And we did show that those numbers are unique, so that's the only linear combination to give you that GCD of 3. And the last thing we'll show in this video, so if we look back at this theorem, it says that we have a way to get the GCD by a linear combination of those numbers. But of course, you can make any linear combination you want. That doesn't mean that's the GCD. But you get a special case with 1. When the GCD is 1, that's kind of an if and only if that you have a linear combination that gives you 1. So if you ever get a linear combination of 1, that does imply that the GCD is 1. That's the only time that goes the other way around. So like if you get a linear combination of 5, that doesn't mean the GCD is 5. It could still be 1. But 1 is the lowest that that set can go. So if you do get a 1, that means that has to be the GCD. So that's kind of a corollary to that theorem 5, that if you have a linear combination giving you 1, then the GCD is 1. And the theorem gave you the other way around with any number, that if it's any GCD, then you get a linear combination of it. So this is truly an if and only if. So I'll just put on the side here, this is actually an if and only if. But for this problem, they want to say, well, if this happens, then the GCD of a lot of other combinations are also 1. And that's because you can view this equation as as picking, something from this side and something from this side, giving a combination of 1, and so the GCD would also have to be 1. So let's write this again, but we'll focus on different numbers. So if I focused on the A and the V here as the original numbers that I'm looking at, and then B and U are the linear combination that gives me 1, this implies that the GCD of A and V is 1. How many other ways can we focus in on them? So to get U and B, I could focus on these two. And so the A and V would be the multiples of those numbers giving me 1. So that would mean the GCD of U and B is 1. And finally, U and V. If I focus on those two numbers, A and B, the original numbers that we're trying to find the GCD of, we can think of as the multiples of those numbers, U and B. And then the GCD of U and V is also 1. So almost every pair involved, it has to be something from this side and something from this side. So we can't say U and A have a GCD of 1 or V and B, but every other combination would have to have a GCD of 1 if one pair does. It's like when we come back up here, this shows that the GCD of 39 and 14 is 1, but it also ends up showing that the GCD of negative 5 and 14, looking at those two, is also 1, because we have a combination of negative 5 and 14 that gives me 1, and other combinations as well, because I have two 14s here, so there's only 2 real combinations in this case, but we could look at this one. Or no, this one doesn't help, because it was 3, so we can't say anything here, even though it is pretty clear that these are relatively prime. we can't really conclude anything if the GCD is not 1. Okay, so this is the first section that will split into 2 parts. So the next video will be the second part of section 2.2.